Welcome back to my Commodore 64 Games Memories video series. This is where I look at old games and some of the technical details behind them. Today we have James Pond 2, codename Robocod, released in 1992 by Millennium, re-released by Kix. The developer was DDS Programming Team. The coder was Steve Williams, musician Dale Johnston, and box art by David John Rowe. I was asked how this game had such large maps, so I'm going to primarily look at that question today. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are all always very much appreciated. I had this game on tape, I think, back in the day, but I'm going to be looking at the disc version today. And let's just open up the disk image in my tweaked version of C1541. We can see that it's got quite a full directory. There are two disk sides to this release. Let's do a little, the command for looking at the sector data. So bpeak, given a track and sector. I just want to have a look at the data that's in this robo-loader file at the start of the directory. So there's the next track and sector, or rather it's the 0 track and length. There's the load address 0324, and then it's got, so 0334 is probably updating the vector at 0324, and then there's some other vectors which are not altered by the looks of that. F1CA is familiar to me, for example. But then it loads some code over here, and then it just runs this code. So it's changing the char-in routine. This is one of the vectors that will get called after something has loaded from load star 8,1 on the basic prompt. Looks like it's just loading a very short amount of code and then just calling it. Usually it points to F157, you see, but basically the vector is being redirected to 334. So I think we can safely say that the code starts executing at 334 in hex. This version of C1541 has been updated by me to include a recover command. What this does is that it scans the disk image for chains of sectors which don't appear in the directory. Sometimes games releases or other releases will have deleted files or hidden files. I think in one of my previous videos, I think it might have been Flying Shark or something like that. This tool was used to extract the level files, because I don't think the level files were in the directory. It's just that the levels were placed on disk in terms of sector chains. So on side 1, there's nothing apart from track 18, sector 0, which is basically the block allocation map, I think, and the directory. That's nothing special. That's not a hidden file. Let's just look at side 2 quickly, see if there's anything there. What was the file name for the side 2 file? Right, so there's no pling, or brackets pling, there we go. So we've got a whole bunch of other files in here. So this is not a single load game. This loads quite a lot of extra data between levels. Let's use the recover command on this. It's just temporary file name, track and sector with %d.bin. Okay, and then stuffing it into a directory. There we go. If I run this command, it will search through, look for unreferenced chained files. And there's quite a lot of unreferenced chains of sectors here. Let's dump all of these into the hex editor, see what we can see. Okay, so there's some data here, but the start load address doesn't seem to be sensible. It's not really aligned to oh, this one is. That starts at A800. Okay, that's that file. That one might be interesting to look at later on. This file, I don't think that's an interesting file. Some of these are going to be fragments of already deleted data or unreferenced data on the disk. That's the block allocation map and the directory. I think it's a block allocation map at the beginning. That looks like a partial directory fragment. Unusual, but okay. Okay, so there wasn't really too much interesting apart from that one file which started at A800. I've forgotten which one it was. Let's go through again. It was this one, yes, T3_1. So it starts at track 3, sector 1. That's where that's where the tool extracted or recovered that file from on side 2 of James Pond. Let's have a quick look at the file data using ChildPad and SpritePad, just to see what we can find in there. Let's load the file into SpritePad first. Let's see what we can find in here. We'll just choose program file, ignore, and then we'll choose the file name, whatever it was. It was D64 recover, file name, there we go. Okay, so there is some graphical data in there. Look, there's what looks like some sprite frames. There's also some other jumbled data which doesn't look like sprite frames. Okay, that's 32 sprites. Maybe that's the entire extent of the data. So 64 times 32 is 2048, which is 0800 in hex bytes long. Okay, I think that's the extent of the whole data file. Let's use ChildPad to import what we think is maybe a character set. So let's have a look. It's not going to be that file. It's going to be ctemp d64 recover and t. There we go. There does seem to be some multicolored character data in the middle of this character set there. Yeah, you see, it does look a little bit like character set data, but there's also some sprite data mixed into that too, and maybe some other data. So, although marginally interesting, I don't think it's terribly interesting to delve into that file in too much detail. Let's run the game in C64 Debug GUI, see what we can find. So because this is a G64 disk image, we get the full experience. There's no, like hacker menu or anything like that, or cracked menu or greetings message or anything. So this loading Robocod thing is at the beginning. There doesn't seem to be any drive code running. It's just running the normal 1541 DOS stuff. We get to this rather nice intro splash screen, DDS programming team, with some nice raster bars there. Very nice colorful screen. Certainly looks very nice, doesn't it? How does it get so many colors? Well, if I move the targeting raster cursor up and down, I think we can see there that it's using different screens. Now, because this is bitmap mode, don't forget that the screen data is actually used as extra color data. Because it's rapidly switching between screens on different raster lines, then basically we're forcing new color fetches for the bitmap mode. So that's like an FLI based screen. This other screen is not. This is just a simple character based screen by the looks of it. Multicolor text screen, yes, character screen, with some sprites for the penguins and for Robocod there, and the text at the bottom. We can see that there's a little raster interrupt, or maybe just a timed color raster based effect, color screen change going on there for the white color in the middle. That's an unusual way of doing it, but okay. We can see where the sprites are. The sprites are overlaid on top of what are chocolate bars. Penguins, the tastiest biscuit in the world, apparently, or something like that. Chocolatist. Okay. So we can see there, the sprite on the right hand side is the animating Robocod animation, just moved off to the side of the screen underneath the border. The code still runs, but doing a very simple animation for it. Okay. A nice little intro screen though. It shows some time and effort went into polishing this game up, which is always nice to see. And then we get this, which is a static screen, which doesn't look too special, to be honest, but okay. It's still going to be loading once we get rid of this screen with the fire button. So now it's loading probably level data, a whole bunch of code. Again, there doesn't seem to be any drive code running at all. It's just doing quite a normal, slow kernel-based load by the looks of it. Zooming ahead a little bit, the game does spend quite a lot of time staying on a black screen while loading, which isn't very good from a usability or a user perspective point of view. Could be quite confusing. Some people might think that the game has crashed, for example. Still on a black screen. It loaded and decompressed a whole ton of data, by the way. That was that whole sweep through memory, reads and writes, decompressing a whole bunch of data. It's still loading data. So I think it loaded all of the game code and stuff like that. And now it's loading level specific data, I have a feeling, because of all of those level files that apparently were in the disk directory, right? So it's almost finished loading. There we go. So immediately we can see that the color bars in the background, if I move the raster beam targeting cursor up and down, we can see that, well, actually we've got two double buffered screens, multicolored text screens for this game, for the top part of the scroll screen. Actually, even when there's no scrolling going on, it's still moving between two screens at 5000 and 5400 in hex, which is unusual. It's doing an awful lot of work for not scrolling the screen, but okay. Anyway, those color bar effects in the background are timed color raster effects for the color bars. That adds an extra dimension of color to this game, doesn't it? Particularly for this level. It looks quite nice. One thing I did notice when I first got this game many years ago was that actually it's not running at 50 frames a second. It seems to be running at a lot slower than 50 frames a second. The scrolling, although it's smooth scrolling, it's not updating every frame. This is where there's some loading going on. You can see from the memory views there that it goes to a black screen, but there's, again, some data loading and decompression going on here. And then we get to the next level, but look here, in the memory view here, we can see from the colorization that there seems to be some map data here, right? That seems to be the previous map, and then this current new map as well. The bright purple bars towards the top middle of the memory view here indicate where the two screens are at 5000 and 5400 in hex. We can see as we move around that the scrolling there accesses what looks like a slightly skewed map. This tends to indicate to me that because it's skewed that way, this map is not quite 256 blocks wide, whereas the previous level map does look like it was 256 blocks wide, right? Because if I remember, this game has the first level map as a huge, great big two towers side by side. In C64 debugger, I'm trying to use the Alt key for fire and then grabbing hold of this thing with my telescopic body leg type skill, and it doesn't seem to be allowing me to grab the top here. So let's go back to now ICU64, because at least the joystick works a bit better. So we've discovered a few little things in here so far, is that we've got this map data in the middle. We're going to spend a little bit more time looking at the map data in ICU64. Here in ICU64, in the debug text screen view, I can see that it's loaded PDS space OB star 8,1 and then sys28672. PDS was a programmer development system, or program development system, I think it was. Quite commonly used back in the day if you worked for a larger publisher who was able to spend quite a lot of money in buying this development system for you. That was great if you could use it. A lot of other games were not built with it, of course. There seems to be a player, copyright Brian Graffiti there. So this handle name is kind of familiar to me. If I do a search in CSDB here, you can actually see this person being credited. Now, there's this release here, which has a whole bunch of music. all-in-one release. There's Brian of Graffiti again. Let's download that and run it and see what we get. Just running this demo release in a new Vice window. Let's have a look at 1000 in hex, which is where that Robocod screen message is. And there we go. Look, player, copyright, Brian Graffiti. The same handle name in the same memory location as well as what was being used in Robocod. So I'm pretty sure that we can safely say here that the person who wrote the music player also had their music player used in Robocod. Cool, right? If we have do a little bit more Googling, we might be able to find a different credit for this person. Just double checking. Yeah, there we go. See, look, we can see all of those. We can see 4 screens, which are color screens being used, the bitmap data there. 2 lots of 4 screens because there were 2 different banks there, so that's 8 screens in total. And if you go back to one of my recent previous videos where I looked at the adventure game was also displaying some of the screens it was displaying were graphical FLI screens. So if we have a look at this page here and scroll down a little bit, we should be able to find, there we go, this person credited as Brian Graffiti for the player. So I think that pretty much confirms it, that the same person was providing, music player code, which, funnily enough, resides at the same memory address. So here's that intro again. We'll just skip that. We're not really interested in seeing the intro in Vice 64. I want to have a look at the level data and try and extract that and see if we can load it into Charpad. That's the goal, is to try and extract level data from this game. See what we can find out. So here we are, back in the game, but in Vice 64 now. To extract this level data, we need to understand how the level data is stored. Well, it looks like there's a map, and the map probably uses map blocks. Looking at this, there are 2 screens at 5000 and 5400 in hex. We can see that they're constantly updated. If I do a watch store for 5000, which is the top left-hand corner character for that screen, we can see, wow, look at that, it's doing a great big long loop for load and store with between the 2 different screens, but with comma X and comma Y. When there's no scrolling going on, comma X and comma Y are both set at 0. So it's copying from one screen to the other and then back again constantly as the game runs. Let's kill myself with the run stop key and then do a watch store now for 5000 257FF, and then let's see if we can find where the screen draw update is being done here. So, okay. Well, it's F8, F9, FA, and FB. FA and FB are definitely updating something. Okay, so that's definitely updating something, data into 5752, and it's copying it from F6A4. But 5752, I think, is the data underneath the score panel, so I don't think we're really interested in that. What we want is that we want the data being updated for the screen. Yeah, we want the top half of the screen. So what we'll do is that we'll just look for stores into the top 256 bytes, 257 bytes actually, of the first and second screen for the double buffered screens there. So 5.4, we'll just put 5.5 there. That's looking for updates. Ah, there we go. This is what looks like a block draw update. So at 1 CDF, it looks like it's loading from the map, doing some address calculation, but look, it's loading from 5.8, 5C, 5.9, scrolling down 5A and 5C again. So 5.8, 5C, 5.9, 5A. So it looks like the block data is arranged at 5.8 while starting at 5.800, and it looks like from this code, it looks like it's using 2x2 character block draws. right? Yep. Okay, so the ASLA at 1CE3 is multiplying the coordinate by 2. That indicates again that it's using a 2 by 2 block draw. So this is in row format data. By the looks of it, it looks like 5800 to 58FF are the top left-hand characters for each block, and then 5900 to 59FF is the top right-hand character for the block, and so on and so forth. This is going to get complicated because I don't think that Charpad will import binary data in this particular format. The Charpad usually wants the map block tiles to be in top left, top right, bottom left, bottom right order, or some variation on that. It doesn't like it in row ordered data. So we'll need to massage this data somewhat. Now, the other interesting thing to note here is that we need to perhaps find out where the color screen is updated, because look, the game definitely has color data being updated as well, but it looks like the color data is also restricted to 2x2 consistent colored blocks. Okay. This color data pattern at the bottom corresponds to the score panel, not the scrolled area. It's just that these what is it? Is that pink, light red, middle grey, light grey blocks? Those are the colored map blocks, but it looks like there's a consistent color for each 2x2 map or tile block, if you like. So to double check and to find out where the color store goes on, let's kill ourselves again by pressing run stop. It's just Robocod. It doesn't matter if we kill ourselves, right? And now put a breakpoint on the color information, right? So the color information for this screen is going to be at D800. That's where the color RAM usually is in Commodore 64. So we'll just look for the top first, 257 byte updates, and there we go. And the color information comes from 5C00. 5C00 is just after the block data, which is luckily enough. So the block data is at 5800, 59, 5A, 5B00, and then 5C00 is block colors. So now we have practically all of the information that we need to be able to extract the relevant pieces of memory from the game and then try and get them importing into Charpad. So let's save out the whole of memory first. So the whole of memory, we're going to try and import that as a 256 width map and 256 high map. We hope that the map data is 1 byte per block, and we hope that it's going to be stored top left to bottom right in row order, basically row column order. So hopefully we'll see that. So let's just save that file. Now the next chunk of data that we need to save out, of course, is the block data. So let's save out the block data at the memory addresses that we've already deduced by inspecting the code and using the machine code monitor to debug into this game as it's running. So that's 5859585B00. So we'll save all of that data. We need to save the block color or attribute data, so color data. So we'll name the file appropriately, and we will save 5C00 to 5CFF in terms of this data for the map tiles. Just noticed a typo. The blocks should go to 5BFF, not 5B00. If you spotted that before I spotted it, then well done. Just copying and pasting this to my debug notes text file. And of course, as usual, I will be committing the text file to source control so you can follow along with the notes that I've been making. And it's also good to help augment my terribly failing memory. So we need to also save out the characters Getting old, you know. Anyway, so the characters for this game are at 4800 in hex, so we will save out the character set data as well. Character set data is usually 8 bytes with 256 characters, so that's 580, or that's 800 in hex bytes long, so that's 4800 to 4FFF. And that should be all the character data. Now, before we try and load this into CharPad, we also need to do the swizzling. We need to update the graphics data for the blocks. So let's load the character set data into CharPad, and we can see that the character set data has successfully imported. No surprise there. It's very simple to import that. Now let's try and import the binary data for the well, we can try and import the map, but we have to set the dimensions for the map first. So the map, we hope that it's going to be 256 by 256, because that's the full 64K of memory. There we go. This text box doesn't accept the value until you press return properly in it. We also need 256 map blocks of 2x2 blocks just to prepare the tile set. For this data, we will expand this window a little bit here like that. Let's get a nice regularly sized window. So let's import what we think is the tileset data without swizzling it around first, so it's not in the correct format for what CharPad expects, and then we can have a look at what we have to start with. And you can see that the block data doesn't entirely look correct. Look, we've got the 4 banks of empty tiles, so I'm pretty sure that data is not in the correct format. It doesn't look like map block data, right? Just realized I have a typo. I need to exchange the row and column order here to swizzle the map data, to swizzle the map tile data around into the correct format. So I'm taking row ordered data and converting it into tile map ordered data. There we go. These look like tile maps now, right? So there we go. And the map data that was imported from the whole of memory is also visible now. It looks like we've got the map data. We also need the tile attributes, was it? No, that's not quite correct. I don't think the tile map attributes were correct there. I think the tile map data, I don't think it should have the 2 bytes at the beginning for the memory address. So let's trim that out in the text editor, in hex editor, by taking out those 2 bytes. So then we don't have the load address. Let's binary import. There we go. There we go. Now we've got the correct tile attributes. In other words, the colors corresponding to the map. So this other data at the top and bottom is just basically the data that was before and after the map in the Commodore 64's memory. But basically, yeah, this is the full first map. So we have 2 towers side by side with correct colorization, correct map tiles, and then obviously the correct character set data. We can see how large this first map is. Now, each of these doors, I think, lets you get to or warp to a different level, right? In Robocod or James Pond 2. So there isn't anything else hidden in this map. You can see all of the map area is used for this first level that you can just move around to select the warp level to get to. But yeah, there we go. I think that's basically all that I wanted to cover in this video is how to extract the large map data and to solve the question of how this game had such large maps. It's doing a multi-load, but it's also storing a large amount of map data in memory with 2x2 character blocks. So thank you very much for watching my Commodore 64 Retro Games videos series. If you like these kind of deep technical dives into Commodore 64 retro games, then please do consider liking or subscribing to this channel, and a super thanks is always very much appreciated if you can. So take care, have a great day, evening or night, wherever you are.